I would like to welcome you to my presentation. My name is David Schimbäck and I'm currently working at Airbus Central Research and Technology here in Munich. Today I would like to present to you parts of my PhD thesis, to be more precise about the investigation on fatigue properties and fracture mechanics behind our additively manufactured scandium modified aluminum alloy, commercially known as Scalmalloy. Presentation at a glance. Many of you might know the concept, so I would like to give you a brief introduction to Scalmalloy, talking quickly about the process technology, the fatigue properties, the cryogenic properties, and give you an outlook. So what's next here at Airbus? So let's do a deep dive into the material characteristics of Scalmalloy. Well, the base for Scalmalloy is the 5000 aluminum alloy series, so aluminum magnesium, which are actually not hardenable. But the addition of scandium and zirconium changes everything. On the one hand, we obtain a hardenable alloy, which is hardenable in a single step heat treatment. And on the other hand, we face a bimodal microstructure due to the highly coherent primary precipitates. This bimodal microstructure, in fact, has a fine-grained area with a grain size way below 1 micrometer and a columnar coarse grain size with approximately 10 micrometers in grain size. The mechanical properties arising from this unique microstructure are quite very outstanding for 5000 alloy series and in fact for most aluminum alloys. So we see a high strength and simultaneously high ductility. We face a high endurance limit, high fracture toughness, and this we obtain after a single step heat treatment without solution heat treatment and subsequent quenching, which in fact is a major advantage for example, complex structures. But we also face some issues with this alloy, especially when processing high magnesium variants. Due to the high magnesium content, we only see an intermediate processability, especially when process parameters are not perfectly adjusted. We also face a susceptibility to stress corrosion cracking. So actually, it's all about magnesium, which seems to be the bad player in this game. If we take now a look at the impact of magnesium onto the process, we see magnesium has quite a high vapor pressure compared to aluminum. This has for sure different kind of impacts. First of all, the chemistry of the alloy is different due to evaporation of this element with the high vapor pressure. Also, the vapor is interacting with the laser and the evaporation of magnesium, and due to the increased magnesium content, the surface tension is decreased. So we increase the melt pool dynamics significantly. And all this is leading to a high probability of material inhomogeneity, as you can see on the right hand side actually. So there are three single layers on top of each other, and already after these three layers we face a material inhomogeneity already. Looking into the future, our former Airbus CTO, Grazia Vittadini, announced our mission towards sustainability and zero-emission aircrafts by using liquid hydrogen as new fuel technique. Therefore, new application and material requirements arise to meet exactly that goal. On the one hand, fatigue properties remain as highly important research and development field for additive manufactured materials. But on the other hand, cryogenic properties gain a lot of interest and attention in terms of our sustainability goal. Start with the investigation of our fatigue properties. Fatigue issue for fatigue is the big scattering due to the process inherent probabilities of material inhomogeneities. Today, we will only take a look at the vertically built specimens as it is the more crucial build direction. So the issue arising with this scattering is the following certification, which can either be only for static loads or for an endurance limit of way below the potential of the material system. In this case, for example, 80 megapascal. But the potential of our material system is up to 300 megapascal, published already in the early stage of our research. Most recently, with perfectly adjusted process parameters, even 360 megapascal were obtained and will be published soon. So, unfortunately, everything else below this kind of 300 megapascal endurance limit is killing the business case for this material process combination. So the evaluation of the defects in detail is crucial. So originating from this big scatter, we need to find the link towards the material and fit this into a fracture mechanic tool. From this point onwards, one can link those material-related inhomogeneities to process instabilities. And as a result, we can improve the mechanical properties by improving the process robustness. But the big question is, which kind of fracture mechanic tool can be identified to be suitable for this topic? We elaborated the Kitagawa diagram for our additively manufactured Scalmalloy. So originating from the various crack initiation sizes, mostly lacquer fusions, and the long crack threshold value, which is approximately 2 megapascal square root meter for an R value of 0.1, we can identify three different areas in this diagram. Firstly, the load where no long crack growth will occur as a function of the defect size. The second area will be the limit of the linear elastic fracture mechanics, as we have already a big amount of plasticity. And the third area will be the area where we are heading towards quasi-static fracture. So the usage of this design tool is quite very easy. If we now detect, for example, a lacquer fusion with 100 micrometers, one can actually say that below this 130 megapascal, no long crack growth will occur, and the material is within its endurance limit. But crossing the border of this 130 megapascal, one will face fatigue crack growth. Even a certain dependency can be seen for the number of cycles. And with regard to upcoming certification, a constant range of defects for a certain machine material combination must be ensured. So, a further tool for finite lifetime is the so-called R curve with the threshold value for long cracks again. In this case, it is only an estimation, but will be elaborated by experimental data very soon and published afterwards. So one can estimate the endurance limit of the material by shifting the no crack growth region towards the observed defect size here. The intersection point with the respective stress isoplates will give us the endurance stress level. When, for example, observing the 360 megapascal endurance level, we saw defect sizes of approximately 10 micrometers, which fits quite very well with the estimated R curve. So, next to the fatigue properties, a special focus will be on the cryogenic properties of our additively manufactured materials here at Airbus. From previous investigations and literature, no embrittlement of aluminum alloys at cryogenic temperatures was observed so far. As you can see here, for example, for 5000, 6000 aluminum alloy series and also for pure aluminum. Only for some states, for example T6, a minor decrease of elongation was observed so far when tested at these temperatures. Testing Scalmalloy in our current heat treatment state, which is peak aged at 77 Kelvin, a different behavior can be observed. The elongation was reduced down to less than 2%, which is an embrittlement of our alloy and by far not typical for aluminum alloys, which leaves us with two main questions on the way to our zero-E application. What is the reason for this cryogenic embrittlement and the fundamental mechanisms behind the phenomenon? And how can we avoid this brittle failure and prepare the ground for additive manufacturing applications in the future? So, bad news first. We still do not know what's the underlying cause for the brittle fracture in the peak aged state, and it's fairly difficult to investigate. But we already found a solution how to avoid the embrittlement, namely by an underaged state. The material response to a tensile load at 77 Kelvin is also completely different compared to room temperature testing, as we see a high amount of work hardening in the plastic regime, as well as we do not see any discontinuities there anymore. Another important topic is actually the sensitivity with respect to material inhomogeneities, which seems to be way more pronounced when testing at cryogenic temperatures. You can see it on the right-hand side on the photographs, where you can see quite very pronounced material inhomogeneities. In order to certify our additively manufactured materials for high demanding application in terms of fatigue and cryogenic loads, still a lot of research has to be done. Especially the fields of fracture mechanics and process technology will be required to enable those future applications. Nevertheless, the tailoring of the material in this special context of Scalmalloy, the replacement of magnesium in order to get rid of the disadvantages of the alloy, is always and was always a special focus of our department at Central Research and Technology. Scalmalloy is the starting point for our journey and by far not the terminal. With the sophisticated process parameter development done, for example, by our colleagues at the University of Innsbruck, we were able to get the grips on the processability and enabled an endurance limit of Scalmalloy of 360 megapascal. Also, with the reduction of the magnesium level to a certain threshold value, we made big progress towards a certain stress corrosion resistant material. Nevertheless, we focus also on further developments in order to understand the microstructure evolution during the process as a function of the alloying composition. Therefore, we developed our second generation aluminum alloy for additive manufacturing called Scalmalloy, and in our second design loop, our third generation aluminum alloy for additive manufacturing called Scalmalloy. And with all those design loops, we focused on the replacement of magnesium and the microstructure tailoring. And the very promising results of these developments will be published very soon. At this point, I would like to thank you for your attention, and I hope I was able to point out our mission towards additive manufacturing applications in the future of aerospace. If you have any questions, you will find my contact information on this slide, and do not hesitate to reach out to me. So again, thank you for your attention.